Please briefly introduce yourselves and summarize your education and professional backgrounds.
My name is Bruce Chalmers. I'm Vice President and General Manager for Jacobs Environmental Solutions business, which is a kind of global platform environmental business, really focused on remediation, of course, the sort of PFAS challenge. I'm actually a civil engineer though, by training, and quite a varied career in Jacobs over the last 30 years. I've worked in nuclear, defence, buildings, highways, and more latterly in the water and environmental space.
And I'm Susan Moiso. I'm also a vice president with Jacobs. I'm also a civil engineer with a master's in environmental engineering. And I have a 37-year career in the water sector, starting and spending about half of that at a utility in Cincinnati, Ohio. I lead a Jacobs team of 9,000 water professionals across the world, and our annual revenues are in the $3 billion range. We think about ourselves as a one water team, and I'd like to expand on that as we go forward. So that's who I am.
All right, thanks. So we're here to mostly talk about PFAS, and as a background and knowing that you're both engineers, and this is an engineering audience where we're in front of here, and then they can handle details and have some familiarity with PFAS. Can you briefly describe what PFAS is and why there's such a problem?
Sure, I'll maybe kick off on this one, Tom. And it's certainly something that's of increasing awareness, hopefully to the engineering community, but also the general public. So PFAS compounds, and there's a very wide range of compounds in this family here, really came into existence as far back as the 1930s. But since the 1950s onwards, basically their applications expanded significantly. And we're still using PFAS compounds in many everyday products and processes today. They're sometimes known as forever chemicals. That's not probably from an engineering science point of view technically correct, and we might touch upon that a little bit later. But I think the reason I call that is obviously the intention of these products and the design objective back in the day was to create products that were highly durable, particularly with respect to water and heat. And such has been the success of this family of compounds that you will find them very pervasively across our everyday lives. So whether that's in the defence industry, aviation, automotive, electronics, pharmaceuticals, food and beverage, they are right around us in all of our lives. And of course, probably, it's only been more recently that we started to get a better understanding of what potential health risks associated with these products are. But of course, because of the pervasive nature, not just across these sectors, but also geographically, because this is a global challenge. Of course, we've started to find that some of these chemicals are finding their way into our environment. And of course, from our environment, they're finding their way into our drinking water. And in some cases, they're finding their way into our food chains. So that should be a concern for everybody, and it's a huge challenge that we all sort of face over the next few decades to try and tackle.
And I want to build on what Bruce has shared with you. And from a water perspective, the challenge is because the chemicals are so pervasive. I like the way that you characterize that. Estimates suggest at least 60% of the U.S. population has PFAS in their drinking water, in their tap water. And we're dealing with it not only from a drinking water standpoint. When it's in the drinking water and it's in the environment, it's also in our wastewater. And when it's in our wastewater and we do wastewater treatment, then we have these chemicals in our biosolids. And so we have to address the challenge across the entire water management cycle, from water resources to our wastewater discharges into our biosolids. So I mentioned in my intro that we look at ourselves from a water team standpoint as one water. And what we mean by that is that in today's water sector, we tend to silo ourselves, and we tend to talk about water in terms of drinking water or wastewater, or stormwater, or groundwater. We really, in order to meet a challenge like PFAS that is so pervasive, we have to look across the entire water management cycle and recognize that all water has value, and that is so complex and interconnected in how we have to approach this.
Okay, that's great. I was going to talk about the PFAS product life cycle. Now, is everything you described what you would consider that life cycle? Is it just the water to water systems? Are there any other systems besides water that would be considered part of the PFAS life cycle?
I think it's probably, quite a bit broader than that in reality to Tom, and it's therefore a big challenge for science and engineering. We probably like to look at it through those kind of three lenses, if you like. The water side that Susan described so well, and that's broad and a substantial challenge standalone, and it's the issue that's facing us right now, getting a lot of attention, quite rightly so, because that's potentially presenting the most immediate risk to health in terms of being in drinking water. But of course, before it gets into our water resources and drinking water, it's probably in our environment somewhere, in our soils, found its way into our groundwater. So we need to, ultimately to look at this problem holistically and sustainably. In some cases, figure out where the point of pollution is coming from, or it could be multiple in some cases, and figure out whether the right solution is to try and treat in situ and remediate the source when it's in an environment, or whether we treat sort of downstream when it starts to get into our drinking and wastewater systems. But of course, really the problem, and this is the third lens, starts with the fact that we have used this product in so many industries, either in the processes or in the products themselves, and we continue to do so today. So if we're actually going to really solve this problem over the long term, we actually have to address that product stewardship piece as well. And this is where, from a Jacobs perspective, it's quite interesting. We're finding opportunities here where we can partner with PA Consulting, which is a kind of a sister organisation that we have investment stake in, and they bring a different set of skills here in terms of material engineering that we can bring together with our market penetration. And really, the first challenge for a lot of these organisations is just to figure out where PFAS might be, and then often very complex geographically dispersed supply chain, who could be working under all manner of different regulations in different parts of the world in terms of components that might come together in the final location. So things like digital technology and data analytics, large language models and AI can be very useful in terms of basically working through documentation and product specifications and various systems to try and identify where the risk might be, and ultimately then help those organisations figure out what their enterprise risk might be, and of course start to strategize around, well, can we substitute alternative compounds that are safer, or if not, what should they be thinking about doing in terms of managing the risk in terms of their manufacturing process with using these compounds, such that we don't let them get out into the environment and of course put at risk our drinking water systems and food chains.
So I'm going to build on what Bruce is saying, and then bring it back to the water cycle and drinking water specifically. I think the most critical point of urgency right now is our drinking water, and that's where PFAS is having the most immediate impact on human health. Significant work to do here. The US EPA estimates that nearly 7,000 water systems will have to take action on PFAS. So I think the good news is that the technologies to remove PFAS from drinking water exist today. For example, activated carbon, ion exchange resins, reverse osmosis membranes, and some of the emerging technologies like selective absorbents that are specifically being engineered to pull out and target the PFAS compounds. And so we help our clients by looking at this from a total water cycle, total asset cycle, from planning to design to construction to operation. So we're very excited also, and Bruce mentioned this, the digital tools. So the digital tools that we have help us to optimize the processes, the layouts, the economics of updating or building a new water treatment system. For example, Replica is a tool that we have that is a digital twin that enables us to build a realistic model of the water treatment process. And then you can start to see how that will operate, how you will target PFAS, and then how can you reduce cost. Beyond drinking water, I think Bruce covered that very well about what's out there in the environment and what's out there from the standpoint of biosolids and how are we going to handle our biosolids from a wastewater treatment standpoint.
Okay, so earlier we did mention that they are often called these forever chemicals, but you're saying that's not really a correct title. These actually can be removed and remediated these days.
Yeah, I mean, I think from a pure science and engineering perspective, um, you could technically say that yes, we can remove and we can remediate these chemicals. But it's the scale of the challenge that we face and the economics and sustainability of the solutions we might need to apply. And, at what level do we try and go to make that, from a point of view of risk and health. Um, but I mean, the Forever Chemicals name is understandable because they are so durable, these products. So it's understandable how that name came around. But I mean, and the reason I talk about sustainability and the scale of it is, again, if you think about how pervasive they are globally across these sectors and how much PFAS compound has been manufactured over the last close to 100 years and is out potentially in the environment, it's a very big challenge because the traditional techniques for the final destruction, if you can remove the PFAS material from the soil or the groundwater or the drinking water, are things like catalytic oxidation, electrochemical destruction, which is basically thermal destruction. Those are highly energy intensive. So they have their own, carbon footprint, from a sustainability point of view. We need to think about it, obviously costly, but also just the capacity of our systems to deal with that type of destructive technology doesn't really exist at the scale of the challenge. So those are proven approaches and they will definitely be part of the picture. But I think where our interest from a Jacobs perspective is probably focused in the longer term is around some of the opportunities for some more nature-based solutions and applications. Now, some of these are not necessarily proven at scale, but these are the ones that, to be honest, it feels to us are more likely to prove some of the more sustainable solutions we use in the future. And what we mean by nature-based solutions, really we're talking about, the use of microorganisms and microbes that can effectively transform these PFAS compounds in situ, in the ground, in the groundwater, and tackle the problem in the environment there. So these microbes will basically use the PFAS as a source of carbon or energy themselves. And the other side of the equation in the same sort of space is this kind of the use of enzymes and microorganisms that can actually break down the carbon fluorine bonds. So again, taking back these compounds to more inert, mineralized compounds that originally were put together to create the initial compound. So these are the ones where we think actually if we can create these kind of biogeoreactors, GRs as are sometimes known, and work on these and move from kind of bench field trials into scale applications, could be pretty interesting because they should not be as energy intensive and you're actually using nature to work the problem. So there's lots of innovation, research and development going out in this space, and I think that will be absolutely necessary given the complexity of the way in which this problem shows itself in the environment.
Okay, so in my research, I came across a phrase called PFAS fingerprinting technologies. Could you describe what those are and how they work?
Yeah, I can, and I think just probably, it's a term that we've used in Jacobs, and you can see it used a bit wider in the industry as well. And really what this is getting to the heart of is that we have tens of thousands of different types of PFAS compounds have been created, and they could be in hundreds of thousands of different types of environmental situation in terms of different types of groundwater, different types of soil, etc. Therefore, the individual remediation situation they're faced is unique in the same way that a fingerprint is quite often, or should be hopefully pretty unique. So we've been, over probably the last 3 or 4 years, putting quite a bit of time and effort into basically what we call forensics, which is a sort of digital tool, which would be in this kind of fingerprinting space that you describe, whereby we can bring together the power of sort of digital, sort of algorithms, machine learning, applied to complex data sets. And these data sets are generated by field investigations and analysis. And then, comparing these to a model, and I'll talk a little bit about the model we built, we can basically, using multiple lines of evidence, narrow down much more quickly than we ever would have been able to in the past to what the likely potentially unique source of that particular compound. So what industry might it have come from? So therefore, what location might have generated it if we want to try and trace it back up a catchment system. But also then when you're in that environment out in the field, we could potentially save time and cost on field investigation and field trials and bench trials by basically having a better understanding of how those particular compounds will potentially behave in a certain environmental condition. So the model, in terms of the data model that we can use to compare the investigative field test results and rates, basically uses literature on 600 or 700 different types of PFAS compounds and their particular patterns. Then it compares to over 500,000 different environmental conditions, then over 100 field trials we've conducted. So that's what we talk about, these multiple lines of evidence that we can compare to field tests. And it really just gets us much closer to the very, very specific source question that we need to answer. We're able to visualize the results in space and time, which is very useful for communicating with clients and stakeholders, and then subsequently design a treatment solution that should be much more cost effective and ultimately shorten that timescale between investigation and starting remediation, which is pretty important given the challenge we're faced.
So now I'd like to talk a little about some current projects and maybe some specifics about those. Are there any that are maybe one or two of your favorite, whether that's from the scope or the importance of a project, or maybe some of the innovation or the complexity of a project? If you could pick one or two and just kind of describe them in as much detail as you would like, that would be great.
Well, I'm going to start on this one because we were just selected for a new PFAS project this week. And so my team is very, very excited about that. In the U.S., we've worked on more than 30 PFAS-related projects in drinking water over the past 5 years, study, evaluation, treatment, treatability, testing, design, and construction. So I'm going to name one. And this one is for the city of Woodbury, Minnesota. Long-term PFAS, we've given them a long-term PFAS solution. Woodbury is in Minneapolis-St. Paul. It's in the Twin Cities area, where PFAS was first detected in early 2000. And we've been working with them since 2019 to evaluate the risk that they're up against. What's unique about this is that it is one that I mentioned the different technologies that we have. It's designed initially to use granular activated carbon, but it's also designed to provide flexibility to be converted to ion exchange if needed, or to have alternative media. So I think what's really cool about this one is that we're meeting the challenge that is here today, and also being nimble with this client and this design so that as things change and evolve with PFAS, that this plant will go forward. And I think that's really important when we're talking about something that is as pervasive as PFAS. It'll be one of the largest water treatment facilities for PFAS removal in the United States. So we're proud of it. And we are at the point where we're going to start construction in November.
From the sort of environmental remediation space, it's a kind of pretty interesting picture from a global perspective, and I kind of give you an example of typically the type of work we do in a second, Tom. But really, I suppose we've been working. I had a book of work here for going back as far as 10 years in the environmental space, and that is genuinely across some private sector clients. Some of whom may not want to talk about it, but they are doing the right thing responsibly in line with what their shareholder expectations are. But we do a lot of work for the federal space, particularly the defence space, not just in the US, but elsewhere around the world. And some of those federal clients have been, investigating, strategizing, and starting to remediate in this space for some time, and actually very helpfully supporting innovation, which is really going to be really important, which ultimately some of the innovations that they're supporting today will probably make their way into scale applications as we really start to ramp up tackling this problem. So we're helping a wide range of clients tackle the issue, but we're also working with some of the regulators as well, because you can imagine the regulation is still quite variable globally. So while there's been a lot in the news and attention around the relatively recent regulations that come into place in the US, we've been working in parallel with regulators in the United Kingdom and creating some tools there as they get an understanding of where their PFAS risk is in their ecosystem, if you like, and how they might approach moving from sort of guidelines and measurement into actually implemented regulations and standards, whether it's drinking water and the wider environment. And I think that's quite important for organisations like ourselves, that we don't just try and sit on the side of the fence. We need to be informed and be able to share even some of the regulatory direction, whether that's between regulators and clients. But one of the, I guess, quite typical of what we do would be maybe a project we're doing up in Canada just now at Jack Garland Airport. So Jack Garland Airport in Ontario, it actually sort of sits on the watershed between two catchments, which has made it quite interesting, between the Ottawa River on one side and the Great Lakes Basin on the other side. And, like many aviation facilities and airports around the world, they've been using, if you go back to the 60s, 70s, 80s and 90s, they would have been using AFFF foams in terms of their fire training, such that they would be ready for any eventuality. So that's not an uncommon practice there. And from around about 2017, North Bay, City of North Bay, they're basically working with a wide range of stakeholders in terms of monitoring, as they started to build up a picture and understanding the fact that PFAS was actually appearing in some of their drinking water sources, and in all likelihood probably coming back to some of these AFFFs at the airport. So that's been going on since 2017, and then in 2022, North Bay appointed Jacobs as their sort of advisor on that project there. So we've been involved since 22, and this is quite typical of what we might do, from very early investigations and strategising around that, looking at risk assessments, starting to develop those early designs and options for how we might treat the issue, working with the regulators, obviously doing treatability studies themselves, again, back to the fact that quite often sites can have unique circumstances. And ultimately, we'll work with that client in the next few years, basically, then procure and actually implement those solutions and do the monitoring thereafter to ensure that we actually do what we need to do. So, that will involve some soil removal and treatment, but it'll also involve some in situ treatment. So we'll do some absorption around hotspots. We'll try and do some absorptions around where it might be exiting, certain water to certain surface water, runoff situations, and we may even do some trials. Like Susan mentioned, activated carbon in terms of how we might, one of the solutions in a drinking water process treatment. But looking at whether activated carbon can be used actually in the field is also something that we're looking at up on that project. So it's a good example of the timescale, complexity, the stakeholders involved, and it brings together the best of science and engineering. And the stakeholder piece is quite important here, because we've got to be able to communicate some very complicated scientific and historical issues quite often to the city, to other stakeholders, to the general public, to communities, etc. And that comes part and parcel of what organisations like ourselves get to do in partnership with our clients on these projects. You have to take people with us on these journeys.
So now I'd like to kind of turn things over to, I think, a very important part of the discussion, kind of the advice section, where we're talking to your fellow engineers. So what do engineers need to know about PFAS chemicals to keep them out of infrastructure and water in the first place?
It's a really interesting question. And of course, the solution here is broader than just what we might class as traditional engineering, because digital skills are massively important here, communication skills into communities and across the science and chemistry behind the problem too. But given how pervasive the problem is, we don't have all the solutions today. And the fact that this could be a 25, 35, 45 year challenge for us all face, actually, you could, you could have a career helping to solve this problem. And to be honest, right now, it's probably one of the most purposeful problems that we may face alongside climate and other things, is to get after this health risk. So I would say that, if people have got some passion and interest around this, it is definitely a global challenge. And the type of careers you have here could be quite creative and innovative, and lots of opportunity to collaborate and partner. But probably this needs to start with being very curious and having a lot of awareness. Just because regulations are varied by geography, even by state, in some cases we may find in the US, the solutions are not all here today. We've got lots of startups, academia, because the regulations are working at different paces, you've got different levels of innovation, pace and innovation around the world. I think it requires engineers to be a lot more curious and inquisitive as to what else is out there, and maybe partner and collaborate a little bit more on the solutions. Because I don't think that, single organisations in single locations of the world are going to come up with all the answers here. And I think it's a great opportunity to sort of collaborate and share across the engineering and scientific community, conferences and that type of thing.
So I wanted Bruce to go first because I wanted to build upon how do we get it into the water? So when it's in the environment, it will get into the water, and it will be in our water supply. We're treating it from a water supply standpoint. Then we have a wastewater question. And even if it is, maybe think about it from the wastewater standpoint, in that, especially in America, we may not have it in the drinking water, and yet in a wastewater system, there is water getting into the sewer system separately. And so you really have to look at this from the whole water cycle standpoint, and you really have to think about this. So I don't feel like it's enough to say, okay, we've checked our drinking water and we're good. We have to think about how then that could be getting into the wastewater, and how do we then look at how we're treating wastewater more efficiently, and how are we reducing the biosolids that we have. And that's something that we talked throughout this about the research that we're doing. One of the ways that we're looking at this is if there are less biosolids for a utility to handle, then that will help this issue, as well as going forward and looking for complete destructive technologies. So I think I really like the way you said this, Bruce, about they need to be curious. I think this is one of those times in our engineering careers where it is good to be curious, and it's good to think broadly and look across this entire water and environment. And I think it's an exciting time for us.
Yeah, I mean, maybe just reflecting as Susan's talking there, at times the engineering industry can be a little bit slow to innovate. And some of the standards that we work to in certain industries have been around for decades. This is going to have to move at pace. The standards don't exist everywhere in the world yet today, never mind the solutions. So again, I think there's that aspect, probably you sort of keep that in mind, that whatever client you're working for, whether it's a federal, municipal, private sector client, there may not be regulations here today that drive them to do something. But as engineers and scientists, I think it's our job to know what's coming around the corner, help our clients future-proof their assets, because sometimes some small adjustments and just thinking ahead here can potentially start to address issues that will start to be regulated down the line a little bit, even though the standard might not exist here today. And at least I think that's part of our jobs, is to sort of educate and help our clients make the right choices with all the information. So again, That's slightly different to some other parts of our engineering industry and the infrastructure world, where it's not moving and evolving so quick that that's not necessarily the case. The clients might be well informed around how their assets are normally delivered, but here they might not know what's coming around the corner. And again, I think that's part of our job as engineers and scientists to try and help our clients navigate that.
All right, thanks. I think that's some great advice for people that are working on keeping the PFAS out of the water. But for how about those engineers working on remediation projects? Perhaps some advice for them on help speeding the learning curve to be able to tackle this large problem, because there are many remediation projects out there.
So I'm gonna take remediation and define it a little bit. I'm going to start with talking about it from a water standpoint, and have Bruce pull in from a remediation, from an environmental standpoint. I think you have to be nimble, and you have to. The science is changing, the regulations are changing, the technologies are changing. Bruce mentioned working with startups who are more nimble, and I think it's also important that we're flexible with our designs, so that as we go forward, and looking at what we've been doing with the plant in Minnesota, putting things in place so that as things change, that adaptive management is possible. I think the whole world is in a learning curve here. We at Jacobs, we've got 9,000 water folks, and then add on the environmental folks as well. That means we're working across the world. We also are part of a group that we sponsor called Leading Utilities of the World, and that's 75 of the most advanced water utilities that connect together, and that connecting together across the world. And as Bruce said, maybe where they are right now, the regulations are not in place. However, connecting and understanding what's being done across the world so that you can be ready for that, and that you're not locking yourself into something that would mean that it couldn't be changed. And just keep collaborating. I think, especially when as engineers, we do tend to, you ask us who we are, and we both said we're civil engineers, and we identify that way. However, to change this, it might mean that we need to think more like the chemical engineers or the digital folks, and I think that's an important piece of this.
Probably a couple of things in terms of, from a remediation specific perspective, and they're not so much in core, qualifications and capabilities that people might traditionally think of here. I think it's, you used the word collaboration there, Susan, but these very complex and unique remediation challenges and environments are very multi-skilled in terms of how they're solved. And the reality is, you won't necessarily take the same solution from the project one to project two. So they take a little bit of a different mindset in terms of creativity and innovation, collaboration, than maybe a more traditional approach to engineering would have taken. And again, I think from the point of view of the learning curve and knowing what's out there, one, engage in your own organisations and push your own organisations to engage with the world that is out there. Get to conferences and contribute to conferences. Let's share what's going on out there. Let's, these solutions, we will all need many of these solutions, and, many of us will need to be very agnostic and have a broad understanding so we can bring the right solution to the right project for that client, and help them, the regular client get to the right outcome for the community around and about. So, just coming up with a solution, thinking we're going to cookie cutter it across 100 sites, probably not going to work. But actually, the solution at a particular site might be unique enough to be applicable in another geography on the other side of the world. But people wouldn't know that if we don't get out and share and communicate. So I think there's an onus on people to, think about the purpose of the mission here, if you want to call it that, and have a much more outward collaborative partnership approach, but also understanding, to say, you might have engineering skills, you might need stakeholder skills, you might need financial skills, you might need digital skills, chemistry, hydrogeology. It's a very diverse range of skills you're going to put together on a team to solve a remediation problem in situ. However, I think it could be, super satisfying to actually know that you've potentially protected and made safe an environment and therefore stopped, potentially harmful compounds getting into somebody's drinking water or worse still into the food chain.
All right, thanks. That's some great advice. But now, Warren, can you share perhaps a piece of knowledge that you learned as you got into doing with PFAS? Maybe something you didn't know beforehand that you now you've picked up and will use into future projects?
Oh, I'll go first on this one. I guess what I've learned throughout all this is the PFAS issue is not going away. The chemicals are pervasive. It's a known health risk. It's increasingly a cause of public concern, and we can't stop. And doing nothing is not an option. It's not an option for us as engineers. It's not an option for our public officials. It's not an option for our people at Jacobs are out there working in these systems. And so that's what I'm taking away from this, is that this is something that I think Bruce set it up really nicely about how long we've had these in our system. And I would say looking forward, it's a long-term solution that we have to find, and we've got to be moving quickly. And we've got to be open to how we're going to collaborate to solve this.
Probably a couple of things, I suppose, just to share. I mean, quite often in organisations such as Jacobs, we might think we have all the answers to the problem, and quite often that is the case. Here, I think it's important that we know what the answer is, but we may not be people that originate and know the answer always, in this back to this collaborations awareness point of view. And certainly that's something that's core to how we're trying to approach this problem. The other thing that I think we need to bring to this is some kind of, realism here, that, the reality in terms of where we can get to, putting aside the conversation we had earlier around, are these forever chemicals and can we technically remediate and remove them all, which theoretically we can, potentially getting to zero in every single environment situation around the globe is potentially not economically or sustainable from a number of other aspects. So we've got to figure out, work really closely between the regulators, private sector, federal, municipal clients to work out what is the right approach here to solving this problem, whether it's up the catchment of the source or whether it's dealing with the pollution once it's got in the drinking water, and make sure that everyone's on the same page to what's a realistic solution that we as communities, and society can economically deliver here over the long term, keeping in mind the obvious kind of health risks. So I think to me that's a sort of takeaway, and something that I think is increasing. That I don't think is a conversation that's completely happened yet out into the industry, but will happen over time. I think when we think about, well, can we substitute? What does that mean? If we can't substitute, what's the impact of that on our wider economic prosperity as a society? This is an exciting opportunity, but we've talked a lot about the challenges and the complexities of it today. But like our mindset and our staff on this is like, we need to be positive about this. We can deliver the technical solutions as an industry. Engineer scientists, we have the capability to solve this problem. We created the problem, we can solve the problem. What we've got to do is just work through focusing on the solutions, not necessarily get drawn into the politics and legal arguments, which will run in parallel. We have no doubt about that, and just be positive around how we can address this. And sure, it is a huge problem, and the scale of it, could be daunting, but we've actually got the tools and the skills and capabilities to do this. None more so than right now with with these sort of digital and AI, machine learning and things that can really help us approach it from tackle the large data challenge that we just wouldn't have been able to after using traditional methodologies 10 years ago. So I think we just need to stay really positive about it. And as an industry, we can do that, bring clients along with us, regulators along with it. I'm sure we can do after this over the next 20, 30 years.